Okay, so welcome back, and now let's do another example. So this time we're going to use the square root of x so as our function, and we're going to do it at x equals 4. Okay, so now, so a is 4 here. So what we're going to do is we're going to do the same thing. We're going to estimate this using the first two Taylor polynomials. So we're going to do the first and second one. So again, we have to take the first derivative and the second derivative. So if we take the first derivative, it's going to be 1 over 2 square root of x. Okay, or 1 over 2 times x to the 1/2. Okay, and then if we take the second derivative, then what we're going to get is we're going to get negative, what? We're going to get negative, negative 1 over 4 x to the 3/2. Right? And then we're going to evaluate these at 4. So f prime of 4, or excuse me, f of 4. Sorry. So f of 4 equals 2. F prime of 4 equals 1/4. And then f double prime of 4, well, what is that going to equal? Let's see. Just want to make sure I'm doing this right. So this is okay. So then if we stick in 4 here, this is going to be 8 times 4 is 32, so this will be negative 1/32. Okay, so now we can write our Taylor polynomials, right? So P1 of x is going to equal so that's going to be again f of a, right, plus f prime of a, right? And so f of a is 2, and f prime of a, f prime of a times x minus a, right? And f of a, which is f of 4, right? And this is f prime of 4, and this is x minus 4. So then this is going to be 2, and this is going to be 1/4 times x minus 4. Okay, now what about P2 of x? Well, that's going to be the same thing as this, right? So I'm just going to repeat this. So it's going to be 2 plus 1/4 x minus 4. Now, the next one is going to be plus what? It's going to be f prime, double prime of a times x minus, divided by 2 factorial. And then we got x minus a squared, right? So we just fill in the a's with what a is, 4, and this is 4. And what is f double prime of 4? It's negative 1/32. Well, what do we get there? This is just 2 in the bottom, so we're going to get minus 164 times 1 minus 4 quantity squared. And there we have our two polynomials. So now, just like in the last problem, they want us to use these polynomials, these Taylor polynomials, to estimate the square root of 6. And then use Taylor's theorem to bound the error. Okay, so let's first estimate, using these two polynomials, let's estimate the square root of 6. Okay, so with P1, we would say that the square root of 6 is approximately equal to what? 2 plus 1/4 times 6 minus 4. So that's just going to be 2, which is going to be what? 2.5. Okay, so the square root of 6 is approximately 2.5. And that's good because what do we get? If we square 2.5, this will give us 6.25, okay, which is pretty close to 6. Okay, now let's use the second Taylor polynomial. So by the second Taylor polynomial, we're going to get an approximation of the square root of 6 by using 2 plus 1/4 of 6 minus 4 minus 1/64 of 6 minus 4 squared. Okay, now, so this is going to be 2, so this is going to be 1, let's see here. So this is going to be 4 over 64, so we're going to subtract off 1/16, right? So 4 over 64 is 1/16. Okay, so what do we get? Well, this is 2.5, right? This part is 2.5. So this is going to be 2.5. So this is going to be 5 halves minus 1/16. I don't have my calculator with me, so I'm just going to do this. So this is going to be 40 over 16. Right? And so this is going to give us 39 over 16. Okay? And I do have a calculator that will do that. So let's see here, we get okay, so that's what we get for the square root of 6 for the second Taylor polynomial. Okay, so now, what do we want to do? Well, we want to find what the error bound would be on this. Okay, so let's take the error bound using the first one, the first Taylor polynomial, and the second Taylor polynomial. Okay, so let's do the first one. Okay, so just like we did in the last problem, we're gonna figure out what R1 is, but this time is going to be R1 of 6. Okay. Now again, let's reason through this. Because of the uniqueness of a Taylor series based on that theorem, the uniqueness theorem, that there exists a C in the interval from what? From 6 to 4, or 4 to 6, such that the remainder, when approximating the square root of 6, by the first Taylor polynomial will satisfy this. So there has to be a value of C that will satisfy this remainder, which is that. Okay? And now, what we need to do is, since we don't know the exact value of C, so we're going to have to determine the maximum value of the derivative, the second derivative here, over the interval from 4 to 6. Okay, well, remember, oh, and by the way, this is going to be the maximum value, absolute maximum value, so, or maximum the maximum value in absolute terms, or absolute value. So this is going to be the absolute value of the second derivative of x. Let's see, of x. Okay? And so this is going to be the absolute value of, well, what is the second derivative? Well, the second derivative was negative 1/4 x to the 3/2, which of course is equal to just 1/4x to the 3/2. And again, since x is, we're only talking about the interval from 4 to 6, so x is positive. Okay, so again, the maximum value that this is going to have is when x is the smallest, which means when x is equal to 4. Okay, so this is going to actually equal 1/32. So that is our m. And so that means that the absolute value of R1 of 6 has to be less than or equal to m over 2 factorial 6 minus 4 squared, which is approximately equal to what? It's going to be 1/64, so 1/64 times 4, right? Because this is 1/32, and so we're going to get 1/32 times 2, which is 64, and then this is 2 squared, which is 4, so we're going to get 4/64, which gives us 1/16. Okay, and 1/16 is 0.0625. Okay, so that's our error for the first, estimating with the first Taylor polynomial. Okay. So this one here, we know that R1 of 6, so the absolute value of this is less than or equal to 0.0625. Okay, so this is our estimate using the first Taylor polynomial, and this is the error, the maximum error, okay, of using the first Taylor polynomial. Okay, so now we're going to do the same thing, and we're going to just now do it for the second Taylor polynomial. So then now we're going to say, again, by the same reasoning, we know that there has to be a c value on the interval from 4 to 6 such that the remainder is going to satisfy this. Oops. Okay, and now we have to find the third derivative. Well, if the second derivative is negative 1 over 4x to the 3 halves, then the third derivative of x, and again we're looking at absolute value, is going to be equal to what? It's going to be 1, oh, not 1. It's going to be 3 over 8 x to the 5 halves. And again, this is going to be minimized, or excuse me, maximized when x is minimized. So when x is equal to 4. Okay. So what do we get when this happens? Well, that means, oh, not 6, 4. So this is going to be 4, and this is going to be 2 to the 5th, which is what? 32. So this is going to equal 3 over 8 times 32. Okay, and I'm not going to approximate that. I'm going to leave it like this because I'm going to stick this in here. So this is our m, if you will. So this is m. So now, our remainder, the absolute value of R2 of 6, has to be less than or equal to, by the remainder theorem, what? It's going to be 3 over 8 times 32 divided by 3 factorial times 2 to the 3rd power. Well, okay. Let's clean this up a little bit. So this is going to equal what? This is going to equal 3 times 8 over 8 times 32 times 3 times 2. So this 8 and this 8 is going to cancel. This 3 and this 3 is going to cancel. So we get 1 over 64. All right, not bad. So 1 over 64. That looks familiar. Okay, so 1 divided by 64 is 0.015625. Okay, so now what does that mean? It means that for the second polynomial, we get an estimate of this for the square root of 6, and it has a maximum error, or remainder, of less than or equal to 1 over 64. So if you want, or 0.015625. And that's it. Have a great day.